The purpose of this video is to explain gas pressure as one of the applications of the particle model of matter. Now, as we have done earlier in this module, we have described gases as consisting of millions and billions of fast-moving particles that move within the large spaces between the particles, every now and then colliding with another gas particle, and then also eventually colliding with the walls of the container. Now, to explain where the pressure comes from, I'm going to do a small diagram here. So let's assume that this is the side of that container. So it's the container wall. And we're going to look at just one little gas particle moving at a high speed. So the gas particle is, we would never be able to see this with the naked eye, but we can imagine this particle coming in at a high speed. It then hits the wall, and then it's going to bounce back after it's hit the wall. Now, we are interested in the position of the particle there, where it's actually colliding with the container wall. So that is the collision. Now, I'm going to expand that diagram. So this is the container wall. I'm going to try and draw it in a 3D perspective. The particle hits the wall, make the particle a little bit bigger, and there's a tiny contact area. There's a tiny contact area there. And we're going to call that contact area A. And let me just redraw that. Call it A. Now, the force of the impact we are going to denote with the symbol F. So F is for force, and A is the area of contact. Now, as we will learn later on this year, in a later module when we do pressure in detail, that pressure is force per unit area. So in symbol terms, we can write it as P equals force over area. Now, in a given second, there will be millions, if not billions, of these collisions. So the more collisions there are, the greater the pressure there is going to be on the system, because this is for one particle colliding. So if we look at the pressure of the gas in totality, the pressure would be equal to the number of collisions per 1 second times the pressure of one collision. And that is why we can state here that the gas pressure is dependent on the number of collisions between the gas particles and the container walls per second. So we can write this in mathematical terms as follows. We can say the pressure of a gas, I'm going to use this little squiggly symbol for is dependent. We use this often in science, on the number of collisions with the container walls per second. So another way of defining it is the force of the particles bumping against the sides of the container cause a phenomenon called gas pressure. We'll accept that definition, but we prefer this definition because pressure is not force, it's force per unit area. But we're not going to be too strict as of yet because we have yet to do pressure in detail. So in your tests and exams that follow, you will at times be asked to answer questions using the particle model of matter to explain certain phenomena, like for instance, explain how a balloon expands when you blow air into it, or what happens to a tire when you pump up the pressure at a service station. And this explanation here is very, very important. So firstly, you say blowing air into a container increases the number of particles in the container. Then the number of collisions per second with the container's walls will increase, obviously, because the more particles that are in the container, the more collisions there will be. So the force on the container's walls increases, so the pressure of the gas increases. So it's as simple as that. So if you have a balloon which only has 2 particles in it, then we would find that the amount of collisions there, let's use little n for number of collisions, would be small. And that's, remember, in 1 second. But if we've got a balloon with more particles, air particles or gas particles in it, then we'll find that there will be more collisions with the container walls per second. So let's represent a bigger number of collisions with big N. But remember, that's also per second. And so here, the pressure of the gas in the balloon would be big, whereas here the pressure would be small because it's dependent on a small number of collisions per second. Okay, remember, per 1 second. And here it's dependent on a large number of collisions per 1 second. And so what it results in is that here the volume of the balloon will be bigger than here. You'll learn more about the relationship between volume and pressure later on in grade 10 when we do gas laws. So if you're asked why is it dangerous to heat a gas in a container, which I often like to ask, then you would refer to this explanation. Heating a gas in a container adds energy to the gas. The gas particles travel at a higher speed. The number of collisions per second with the container's walls increases. The force on the container's walls increases. The pressure of the gas increases. And if the pressure becomes bigger than the container walls can deal with, the gas bottle will explode. You see, gas bottles are rigid containers. So unlike a balloon whose container walls can expand and contract as the pressure varies in the container, with this rigid container, you've got to be careful because the container walls cannot give because they're not elastic. So eventually, if the pressure is too much, they will explode, and therefore that is dangerous. Lastly, pressure. Gas pressure is measured in different units. The atmosphere is a unit that refers to the standard atmospheric pressure at sea level at a specific temperature, 0 degrees Celsius. There's also the unit pascals, the unit psi, the unit bar. 1 bar is 100,000 pascals, but you'll learn more about this in the module later on in the year on pressure. So I hope that this short video has helped you to gain a deeper insight into how we can apply the particle model of matter to explain pressure in gases.